So, I'm Fran. I mentioned I've written a book. Did this already, didn't I? So, I'm going to think about randomness. Brief mention of testing, particularly property-based testing, which will just be a zoom through. I'm going to draw some pictures in C++. My book's about machine learning and genetic algorithms. I think a lot of people, when they talk about this at the moment, are focusing on using frameworks and doing really, really clever, hardcore math stuff with neural networks to spot cats in pictures. So I've strayed away from the hardcore maths to spot cats and basically simplified lots of things down to for loops and while loops, where you get to see things move. I edit the Accuse Overload magazine, so if you get inspired to code your own way out of a paper bag or similar, send me an article, email there, or just share any fun pet projects you're doing. But as I said, this is all about coding your way out of a paper bag. Why? Well, Jeff Atwood ranted about this. I was interviewing some candidates some years ago, and one of the people who was interviewing with me came out of the room and said they couldn't even code their way out of a paper bag. And I thought, I don't know what that means. How do you demonstrate you can code your way out of a paper bag? At that point, people usually start talking about FizzBuzz. And I don't think FizzBuzz usually conventionally involves any paper bags at all. So that can't be right. So I thought, what sort of things could I use to program my way out of a paper bag? And I went through my head a list of some machine learning techniques that I knew a little bit about, and I thought, what sort of inputs do they take? Some of them take numbers, some of them take words, some of them are more free form. How do they learn? Whether this needs one batch job and it learns something once, or whether it keeps redoing things over and over again. Don't talk to Steve about k-means clustering. Whether that's learning or not is a big question. Some of these algorithms involve doing something random. Sometimes they don't. Some of the outputs, you get some numbers out, or maybe you get data points out. And if you get data points out, then you're doing something in space, so perhaps that works. Would it escape a paper bag or not? Well, I chose the last column, and I thought, wow, see, I don't know what to do. But my PhD was about decision trees, so I put my previous data set through a decision tree and went, oh, right, yeah. It seems to me that I seem to think that if I do something slightly random, that I can code my way out of a paper bag. Don't know if you've spotted that in my big table on the last page. Decision trees are great. There are loads of ones out there already implemented, and there's a chapter on it in my book. It's quite a nice way of collapsing down some complicated-looking data. So, long story short, I got some people to sign my award, so I have a certificate saying I can program my way out of a paper bag, so that's good. I've done this in a variety of ways, all completely over-engineered, and this is totally self-indulgent. I want to go away and learn about some of the techniques I know. There's something to be said for trying to implement something yourself. You understand it better if you do that. So I've looked at ant colony optimizations, several genetic algorithms, and some particle swarms, and more besides. And then, did I mention I wrote a book? I mentioned that. All right. So I decided from the decision tree, if I do something random, well, besides anything else, it'd be more exciting, something slightly different to happen every time. And then I can watch my own demo and go, oh, didn't notice that before, so that's good. What we're going to do today is a Monte Carlo simulation. Now, technically, that's not part of machine learning, but you'll see people talking about Markov chain Monte Carlo simulations, so it's going to bring in some words, and then you won't be blinded by science when other people talk about them. What do we use Monte Carlo simulations for? Well, suppose you had a hand-drawn squiggle. You might observe this squiggle isn't actually hand-drawn. I've drawn this in Python using the XKCD style plots in Matplotlib. It took hours to try and make a curve look hand-drawn programmatically, but that's another problem that we don't need to talk about today. What's the area of this squiggle? It's less than the area of the rectangle, and it's more than 0. So we've got some bounds. I could fill in some squares and just see which have got some in and which haven't. and narrow down the bounds a bit more. Or I could just chuck darts at it and count how many are in and how many are out. And that would give me a proportion of the larger rectangle. If I do that a few times and take an average, I've just made a Monte Carlo simulation. There'd be some mathematical bounds on how many times I need to do this to get an accurate answer. But the idea is, instead of trying everything, with the rectangles, I can make them smaller and smaller and smaller until I get down to pixels. We haven't got time for that. We're too lazy. This sort of thing, just try it, see what happens, get a vague idea. So that's what we're doing today. So we can use Monte Carlo simulations for trying to solve a problem, like that squiggle just now, but we weren't sure what the area was. We can't do any maths on that because there wasn't a formula to do the boundary of the squiggle. So sometimes you can't do the maths. Sometimes you can't be bothered to do the maths, or it would take too long. So approximate answers. You can estimate pi, and I know for a fact there's at least one or two people in the room who've used Monte Carlo simulations to work out what pi is, even though we can already find it in other ways. It's fun. Why not? And you learn things when you do this. Another thing that happened with some Monte Carlo simulations is you could change the squiggle or change the model you're using. Say, what happens if I make this bigger or smaller? If you look at the spread of infectious diseases, for example, malaria, if you guesstimate how much you change the probability of the disease being passed on by introducing, say, mosquito nets into one area, you can work out the best ways to try and reduce things spreading just by twiddling some parameters if you've got a good model. So it shows you what would happen if I did this. Is it better going down or up, left or right? Down or up, left or right? We might be able to get something out of a paper bag if we did this. So, what history of Monte Carlo simulations? Loads of things date back to the beginnings of nuclear wars and threats thereof. So, this guy, Ulam, was working on the nuclear weapons project. Really, it's called Monte Carlo simulations. Monte Carlo casinos, gambling, yes. He was recuperating from being ill and trying to work out the maths of how likely he was to win at a particular type of patient. And then he thought, hang on, I can't manage to do all the maths. It's too much effort. What happens if I simply observe and count how many times I win? So if you win every other time, that's about 50% chance of winning. So use some probability for this. And he immediately thought of other problems of neutron diffusion that he could solve using this. So we've got some diffusion in here, so it's definitely relevant to the talk. So diffusion, something spreads out. They're different models depending on whether you do it in gas, solids, or liquids. We'll stick with a simpler one in gas. If we were to put water or cement into a paper bag, it will probably go horribly wrong. So we're not doing that today. It's about things spreading out. I'm in fact going to try out three things. We're going to try the simple model first, which is Brownian motion. Then we're going to do advanced things. That means some multiplying as well as some adding up. It's going to be good. And then we're going to do jump diffusion. Three things. What's time? Oh, plenty of time. What's it got to do with paper bags? Well, I'll show you the model in a moment, so there will be maths. It's quite simple, really. We're going to have a paper bag. We're going to have something in the paper bag, and it's going to spread out. It begs loads of questions. Can we go off the screen? We probably can. Can we go through the sides of the bag? I don't know. This is a dreadfully underdefined problem, coding your way out of a paper bag. We don't know what colour the bag is. I don't know if that makes a difference. I have done some experiments with some real paper bags, and I think the brown ones seem to be easier to... Well, I've tried some little robots. I'm not a hardware engineer. I'll leave that to you to decide. The bags today are going to be brown. So basically, anything like this, you just need to think slightly laterally. I mean, you could put a maze in a bag. So the bag is the brown rectangle around the edge. If I put a maze inside it, then I can do a maze-solving algorithm, and eventually out of a paper bag. So you just need to start thinking laterally, get your imaginations going. Let's introduce this maths model. Anyone come across the idea of a random walk before? Cool. So, I'm where I am now. Simplest type of walk, I could go one step one way and be blinded by the shiny light. And I promised the recording guy I wouldn't move too far, so I could go one step the other way. So if I can just go one step left or one step right, and each is equally likely, on average, I haven't moved at all. Which is one important property of a random walk. You can do more complicated things. I could go forwards and back as well. But the simplest case is just along a line, all the steps the same size. Do advanced stuff today. We're going to go up and down as well as across, and we're going to have varying step sizes. Amazing. And now we can start to put this formally mathematically. It's called a Markov chain. All that means is what happens next just matters where I am at the moment. It doesn't matter whether I've gone right and left or left and right first. We've forgotten the past. We just are where we are now, and we take a step. Or another step. I said that, well, it's continuous as well. There are no jumps. I'm not going to teleport off somewhere else. Though I will do jump diffusion right at the end, so we will introduce some teleporting at that point. I said that we're equally likely to go left or right. So on average, overall, we get an expectation of 0, which is this E of the steps over time being 0. So overall, we're going to see some blobs moving out. If you kind of look at them, they look as though overall, if you averaged the amount of movement, they stayed where they start. But we need this one important property for it to be Brownian motion properly. You need to do the variance of the step sizes, keep that to the time step. Basically, if you don't make it big enough, everything will stay bunched up and it won't diffuse and spread out. If you make it too big, things will zoom off instead of diffuse. I mean, if you want to code you out of a paper bag, then zooming off is fine as well, but we're going to do the Brownian motion diffusion. And this just involves bolting the right parameter into our random number generator, and it'll just work. So, we're going to walk one step at a time. We're going to vary the step sizes and use normal Gaussian distributions. You could just do it with uniform numbers as well. It'll work. But you probably want them to be smaller. Any direction's equally likely, and Markov. What happens next only depends on where we are at the moment. So, here's the maths. I said there'd be maths. We want some steps. So, if I describe a point as being an x-coordinate and a y-coordinate, the x step is going to be the square root of time, which is just a number we'll make up, times a random number. It's usually dw, the Wiener processes in the literature. That just means a function that gives you a random number. I'm going to pick from the Gaussian distribution. It needs to have a mean of 0 for the Brownian motion. We'll move on to more advanced things that have a mean that's greater than 0 when we come on to geometric Brownian motion. So all I'm doing, that gives me back random number times my step size, and I just add that to my current x position, and then to find the change, or delta, that's what the delta y is, the y position, again, the square root of time times another random number from my function. That gives me what to add to y. So everything can move. We're going to do this with several blobs, and we're going to watch them spread out. It's a reference to Hull's book on futures and other derivatives there if you want to read more. Just picking a random number, doing some adding up. It's fine. Brief segue first about, so you'll see talks about Monte Carlo simulations start talking about stochastic processes. Don't panic, that just means random-ish. Anyone used old school C's rand? Anyone love it and think it's really easy to get right every time you use it? As I'm getting older, I have to concentrate more and more, and it goes wrong. I mean, I mentioned about the uniform random thing. We want maybe +1 or maybe -1. We want some normal random numbers this time. Trying to get those out of rand is a bit of a challenge. And then we'll mention Mersenne twisters. Why do we want random numbers? If we go back to this hand-drawn squiggle, if instead of randomly just throwing darts at them, you constrain them slightly, you'd get better coverage, but we haven't got time for a diversion to low discrepancy numbers. Okay, so if I'd got one's continuous, one's discrete. Uniform, if I'm rolling a dice, I want 1, 2, 3, 4, 5, 6. And I want each of them to be equally likely. So that's being uniform in the sense that each of them is as likely to turn up as the other. I get a 1 in 6 probability of each. If I'm modelling other things, the typical example in the books is people's height. I've then got continuous numbers in theory. That I get all very philosophical quite quickly. What you tend to get is most people around the average, and you get fewer people at the extremes. So the bell curve, yeah. So it's just different probabilities. The uniform one, everything's equally likely. Step up to bell curves, and then there are lots of other distributions. That's all. You can actually make the bell curve out of the uniform numbers, but that involves some maths. And you might as well use C++11's random number library, because you'll probably do it wrong if you don't. But yeah, if you're rolling dice and you want everything equally likely, that's uniform. Yeah? And then the bell curve, things, like I said, for our stepping around, we want 0 to be our average, and we want equally likely left or right. But maybe not giant steps very often, but occasionally that's allowed. So it's going to be nice bell curve shape. And then to look like diffusion. As I said, there's this other method called Sobol numbers, where you sort of mess around and it's kind of random but in chunks, but that's a very long story. How do you get random numbers out of a computer? Is anything actually random? Did I mention my undergraduate degree was in maths and philosophy? I'm going to distract myself and bring myself back on focus. Yeah. How do I get a random number? Well, I either look on XKCD, or in this case on Stack Overflow, and in the comments. Perfectly picked random number. There was a recent Verity Stob in the register, and she was ranting away about random numbers. It was hilariously funny, but again, not time for that. Seriously, so C's rand is not good for serious random number generation. Of course, even C++11's random numbers are really cool and useful for the kind of thing we're doing today. If you want some hardcore crypto stuff, they're not, but that's another topic. It might not be thread safe. I'm not going to do any threading code today, but you could with some Monte Carlo simulations, so be aware of that. And yeah, there's the history of things that have got horribly wrong. Simple question, so using rand, how do I get a number between 0 and 100 inclusive? That's like my dice roll between 1 and 6 inclusive, but we're going to go like this one, from 0 and up to and including 100. Nope. Does that ever give us 100? What else goes wrong? Yes, unpack bias slightly. Yeah. Yeah, you'll get some numbers more often than others. So for the dice roll, if I do things modulo 6, I'm going to make some numbers more likely to. If you see anyone slamming a modulus near rand, then it won't work. Is that better? Can I get 100? Yeah, guy's face, like, I can't, oh no, do I need to add 1? Where do I put the 1? I don't like this. Oh, yuck. That one? Do not laugh. It's called rejection sampling. That one works. It might take longer than is entirely necessary. Yeah. But it's got a name and everything. And actually, like, that was what you used to have to do, but now we can rely on the newer libraries to deal with us. So we already noted you can't get 100, and we don't actually get our uniform, equally likely distribution of all the numbers that way. And in fact, we don't get 100 here either. There needed to be an add one, or is it a take one? I can't remember anymore. It's just too horrible. Rejection sampling, yes, we got 100 a few times. Didn't show you how long it took. So, rolling a dice. Is this right? Oh, question. I think I ran that on a version of Visual Studio some years ago, so it was probably 2013. Yeah, they're all terrible. Yeah, I mean, I could do some more stats on them. But yeah, RAND is terrible, and some RANDs are more terrible than others. So rolling dice could do this. Are you absolutely sure you're never going to get a 7? See, we're having to think too hard. I just can't do that on a Tuesday. I think it's all right, but I don't remember anymore. We could do this instead. This looks kind of angle bracket and slightly spiky at you and angry. But we can be explicit. I want some uniform ints out of this. I want them to be between 0 and 100 inclusive. I always have to concentrate on that bit, because quite often in C++ you do the one less than or end, but this one is being inclusive, I think. And I have a generator. There are a variety of different generators. This MT is a Mersenne twister that I mentioned before. You seed it. We know about seeding random numbers. We know why. I'll unpack that slightly in a moment if we're not sure. And you just call your distribution with your generator, and it gives you a number back, and then you can play a role-playing dice game or something. Yes. It can. And also, sometimes the random device seed generator just gives you the same number back each time, which is with, yes, so things can go wrong. You need to think about how you're seeding things. And I've got some questions for you, because I'm not quite sure. When we move on to the jump diffusion, I want some Poisson distribution as well as the normal ones, and I don't know if I should use the same generator or not. I don't know. But my blobs get out of the paper bag, so that will do for today. So just a reminder about the seeds, the old school stuff. It's quite simple, it works, but it starts repeating. It's called a linear congruential model. Kind of, in essence, your seed's your first number, and you do this linear bit, which is just like the y equals mx plus c curve, so multiply and add. And then the congruential is when you take the modulus, so that jumps you to another number, and then rinse and repeat, make the next number from the last number. But these then start cycling. As soon as you hit a number you've already seen once, well, you know what's going to happen next. Because we're just multiplying, adding up, dividing, looking for leftovers. Mersenne twister's kind of doing the same thing, but it's doing some larking around with some bit twiddling and muckiness that I can't remember the gory details off the top of my head. It's based on a Mersenne prime, which are all of a form 2 to the power of something, take 1. Someone's recently discovered a new Mersenne prime that's got millions of digits. It's quite amazing. You can look these things up if you want to, but they're just there. And actually, if you just peruse the C++ 11 random number library, you'll see loads of terms like this. Under the hood, multiplying and adding up, it takes much longer to repeat than the old school linear congruential one. So, why is it called this? Apparently, it was originally a primitive, twisted, generalized feedback shift register sequence. And Knuth spake and said, that's a bit of a mouthful. Shall we just call it a Mersenne twister, as we're doing some bit twiddling and stuff? And anyway, that sounds like a jet coaster, so that's quite cool. So, Mersenne twisters for you. Anyway, I was supposed to be diffusing my way out of a paper bag, and I've sidetracked myself completely by random numbers. I was going to go for some normally distributed ones, so we looked at some uniform ones. You can make things that are approximately bell curve normally distributed from uniform random numbers. Couple of ways. Would you feel confident about coding that up? We could just change the code we saw before and we just say normal distribution instead of uniform. And then it'll do our bell curve for us. And nice and simple, good. With all the caveats about thinking about how we see things and stuff. It's good enough for coding your way out of a paper bag. You might need to be more careful if you're trying to value things or do something serious with a Monte Carlo simulation. And yeah, watch out on some setups. If you use random device, you'll just get the same number back each time. So lots of things can go wrong. Basically, you need to test your code and check it's doing what you think it's doing. Finally, right, I'm getting there. So we're going to have some air in our paper bag. And it's going to... We'll tell it how big we want the steps to be. That was our root T in all the maps we had earlier. We're going to send in the seed, because we've already said this all gets quite mucky. And I made all kinds of mistakes, but I think I fixed them. And then the actual maths we want, this is our root T times our dW. So it's quite over the top for some multiplying for us, but it means I can have something that's providing the bump, bumping all my green blobs around, and they'll eventually move out of a paper bag. They're green blobs, let's call them particles. I said we're at one position now, X and Y, and something's going to bump them from the outside, the air, and they'll just move the X and Y by the step we've got. So, slightly squashed. I've used the SFML library for this. Don't know if anyone's come across it before. It's really cool. I spent ages coding my way out of a paper bag using other languages. I'm too scared to draw pictures in C++. I don't know how to do this. All these big libraries for games and things look really scary. Actually, they're not, but this is quite a nice, simple way in. So, get a window, possibly handle some key presses, draw some stuff on the window. So, like I said, I can pause the thing, and here's my coding my way out of a paper bag, bit of code at the bottom. I'm going to have a bag, so I'm going to draw 3 rectangles. You can figure that out yourself. If you desperately want the code, if you go to the pragmatic bookshelf, you can get the code even if you haven't bought the book and have a look at it. You might as well just try and build it up yourself. I'm going to have a circle shape, which I decided to make green, because I'm going to diffuse green blobs out today. And I'm going to choose a number of particles, actually set it up so I can send this in from main, so I have loads or few. And I'm just going to bump each of the particles by however much the air decides to bump them by. Remember, that's just returning us our random number times the step. I could change the step and then it would go bigger or little steps and it do smaller moves. And now I can pull it all together and the demo will definitely display on the screen, unlike the lightning talks faffing around that happened. So, paper bag, my 3 rectangles that I left as an exercise to the reader to fill in, green blobs moving. Look, it's just some random numbers going on. I think if you look at them, you can see they are still, the average is still where they started in the middle. And they are spreading out, because we did our proper maths, we used root T, so it doesn't zoom off, doesn't stay clumped up. They are spreading out at quadratic variance. I've set the code so as if they get near the top, they'll just stop. So we want some blobs out of the paper bag. Is the one on the left going to go back in again? Exactly. I see. Well, Jeff Atwood didn't say whether you're allowed to go through the sides or not. Oh, there's loads of other things I could try. Yeah, or like a joint talk or something. It would be great. One out, yes. Yeah, they're definitely like going out and then go back in again, but they're spreading out, aren't they? Just from some multiplying. I think there are about 25 of them. I think we've got one that's gone, all right, now I'm out. If we keep going that way, I'm done. This might take a while. I timed it once, and it does take about 20 minutes or so for them all to get out. So I quite like sitting watching it, but maybe I did promise 3 types of model, so probably better move on to the next one. Also, going through the sides was mildly annoying. So I set it up so as I could stop that happening. So have, say, 25 particles again, say, no, do not go through the sides. So all very similar. Well, I just go, wow, if that's, do some edge detection. If I'm going to go through the edge of the paper bag, it doesn't get to move that time. And that had the catastrophic effect of meaning that sometimes they didn't move in a time step. And this one takes even longer for them to get out of the paper bag. I'll give them a moment, and if I remember the right parameters, never do command line parameters that aren't named, because then you can't remember which one's what. That's a dreadful way to write code. But hopefully none of them are going to sneak out the edges this time. Just from some multiplying. That's quite amazing. Oh, I didn't see it. Prove it. It's not actually gone out. It's kind of hitting against the side and not quite. It's possibly denting into the edge slightly. I mean, say again. Say, it wasn't a particularly branded bag. It just happens to be brown. Yeah, we should be doing that. And the other thing that this Brownian model does, or doesn't do rather, is it doesn't detect them hitting each other. So there's loads of things we've not done. We've just simplified it. But lots of the Monte Carlo simulations or any kind of mathematical modelling is you say, well, assuming the spaceship's got 0 mass and other things, try and make it simple, because otherwise the maths gets really mucky. Simple is good. I did say this. This made it take even longer, so... Still quite mesmerising to watch. They still are spreading out, but I've messed with the Brownian motion by doing the edge detection. So, Brownian motion's a specific type of diffusion. Diffusion's about things spreading out, and the simplest one you can do is this gas model one, which is just multiply random number by the root of the time. So we're going to do some geometric Brownian motion in a moment. In fact, we might move on to it now, because this is taking ages. That was just the thing I called step, which wasn't quite right. I should have called it time and then taken the square root. Basically, in the code, I got step times the random number, so I can send it in from the outside and they'd just do bigger steps as they went. So I can configure, I can change the speed at which time runs at. Say again? It would, yes. Yeah, it's completely pointless. Might as well make it 1, and I think it is in fact 1 in my code. So yes, that's unnecessary multiplication. Just being consistent with the literature. on the multiplying and coding your way out of a paper bag. One of them's got out. This has slowed it down. Oh, this is terrible. And we're over halfway through, and we've got 2 more types of things to do. Right, so eventually we got some things out of a paper bag. So can we go through the sides? Are they allowed back in? I don't know. Well, configure it. And then we stop them going through the sides. We've made all these assumptions about whether the paper bag's permeable and the temperature. Of course, if you made it really hot, then the paper bag would catch fire and there'd be no paper bag, which may or may not count. I do not know. Too slow, though. Takes ages. Just mentioned setting fire to the bag might not be on. So, stock prices, they always go up, yes? Okay, where's the paper bag this time? Well, you could, if you think laterally to your paper bag as being like a time axis over time, if I plot the stock price and it goes up in a kind of wiggly, random walk, diffusion type way, then it might get out of a paper bag. Gratuitous kiss and picture for historical reasons. So stock prices are about supply and demand. They're not a prediction but a convention according to Keynes. So let's predict them using a Monte Carlo simulation. There's lots of assumptions behind all this. It's simplified, of course. Now, last time we had a DW, which came from the random normal distribution. Got some DW again in here. Square root of time steps still, which is controlling how much the wiggles are, just like in the last one. But now we've got this extra part. We've got a mu times the time step. If you invested money in a risk-free investment with compound interest, like, I don't know, 0.25% or something, you'd get an exponential curve going up. So what the stock price is doing, the drift, this mu times the time step, is like the compound interest, curving up, but the DW is just going to make it wiggle around a bit over time. Exuberance is one word of doing it, and dispersion, wiggle is the word I chose, but that isn't the one that's used in the literature. Oh yeah, we also built into this the volatility. So that's another way of scaling how much it wiggles by. Which begs the question, how do you work out how volatile it is? So we want some drift, so that's like our interest rate, so we need a number for that. Do the banks use LIBOR anymore? Oh, they're in the process of ripping it out of their system as people lied about LIBOR. So we're going to use something else, and that's not going to go wrong in any way, shape or form. How do we find the volatility? We can look at the historical prices, assume your model's right, put the numbers that actually happen back in your model to get the value back out. But that assumes your model's right. But because you have to keep redoing that, your model probably isn't right. So or you can use complicated other things, or you can just make it up. And because we want to code our way out of a paper bag, I'm just going to twiddle the parameters desperately till it works. It's going to be fine. Yeah, talking about the machine learning, so we want some drift and some volatility. Just need 2 numbers, maybe the step size. We've seen some of the number of parameters some of the machine learning and AI models use. This was quite an interesting little story. An AI was drawing quite realistic photographs of people, and they looked really convincing. But it apparently had about 26 million parameters, and no one could actually repeat the experiment. That's a lot of numbers to choose. So, some code. We're going to have a stock price simulation, and it's going to start with one price, and we need our drift, our volatility, and the seed and this DT, or the step size that we had before. And this time, we're going to do some multiplying and adding up, slightly more complicated. Still the same thing though, get our stochastic number, random number, from our distribution, which gives us the increment. We've still got the dw and root t going on, but now we've got the drift and the volatility as well. Multiply them together, and that's the step size that we move by. It's just a way of having the drift upwards in there and the wiggle, not the proper technical term, it'll do. What can go wrong? Oh, yeah, that seeding. Some versions of Visual Studio got a major strop if you use 0 as a seed. That's ridiculous. Yes. And if I'm going to do a simulation of like 10 stock prices, instead of using random device, sometimes people use the current time. If you do that in a tight loop to set things up, you might spend 10 minutes going, why are all my stock price simulations identical? Oh yes, I put the same time into each of them. So there are lots of ways of things going wrong. How do we test this if things can go wrong? So I quite like Phil Nash's catch framework, which is now updated to catch 2, so you might have to twiddle the code slightly to get it working with the newer versions of his framework. When you have things like this, you're in danger of just testing, do I wanted a random number, have I got a random number? And you're not really testing your code. If something different happens every time, how do you deal with that? Well, you can clamp the seed down and check the exact sequence of numbers. But then you're sure it's really doing what you need it to be doing. So you can start thinking about what properties I've got out of the simulation. If my stock price starts at 0, well, the amount of drift up is, it'll stay at 0. If there's no volatility, then I'll get the drift back. If you change perspective on things and start thinking about some of the properties you need, well, you can write a test like that, but then you've got some random numbers in it. Hard-coded random numbers that you made up off the top of your head. If you can find a good property-based testing framework instead, that could fill in, kind of like doing a Monte Carlo simulation to try and break your code. That could choose, instead of some hard-coded random numbers for one test case, it'll try loads for you and might find some errors. So I had a little play with the property-based testing framework. I think there are probably some better ones out there. And this is kind of a cry out. If someone knows a really good C++ property-based testing framework, come and tell me about it, because these things are cool. If anyone does Python, the hypothesis framework is really good. But that's an aside. So I said, if I start thinking about some properties, like start at 0, we remain at 0, and so on, we can get some good tests. The original property-based testing framework, I think, was it quick check in Haskell. So basic idea, I've got a vector. If I reverse the vector and then reverse it again, I'm back where I started. So that's the hello world of all property-based testing frameworks. So it's obligatory to have an example of that. What happens is, if it fails, any of these fail, it'll tell you what numbers it was using instead of your magic numbers that failed. And at least you can then flush out some unit test cases or something. So this is a really good way of exploring, particularly things with random numbers in. I've got an example in the slides that shows one that I used a while ago, but I might just zoom through those, show us the simulation. Just wanted to throw out this property-based testing. So you set up what sort of numbers you're willing to accept and what you expect to happen. And then you can send out some fail messages telling you what numbers went wrong. And now let's do this stock price demo. So this time we were doing some drift with some wiggles. I've got time on one axis and the stock price on the other, which will look remarkably like the paper bag in the previous demos. And they may or may not get out of the paper bag. Got a batch file this time, so I can't remember which parameter's what. Oh, look. So, several curves, several simulations running. 12, I think. Don't know how clear that is from the back of the room. So you can see none of them have got out of the paper bag. If I turn up the drift, they might go up a bit higher, so we can now start playing with the numbers. So that was 40% return on our investment, and over the width of a paper bag, we haven't got out. But we can twiddle the numbers, and then we can get out of the paper bag. What else have I got here? This one sometimes gets out. So this time I've jumped up the drift to 50% and given us 30% volatility. So way more wanging around. And it still didn't get out of the paper bag. Sometimes does. It's closer, and we can keep playing this game, and we can try the parameters until it gets out. We could turn off the volatility, and then actually we could do some maths to work out the return we needed to get it out of the paper bag. Yeah, we could start doing some maths on that. I haven't. That one's out. There's no diffusion this time, though, so I feel like I've cheated at this point, which just about gives us time for the third model. I said earlier on that these were essentially continuous models. We didn't teleport into hyperspace. We've got some strict mathematical properties on what happens here. At any one point, you just move a step for a definition of step, which might involve all this root t and some maths proofs with epsilons and deltas. But if every now and again I go, now I'm going to kind of toss a coin, see whether I jump or not, and if I jump, I'm going to do a huge step. I promised James I wouldn't jump around, so we'll do it on screen instead. So we can take the code we've got, and we can add in a jump. For those of you who are paying attention, the formula at the top is remarkably like what we had just now. We've just got this plus j dn. dn's are like the dw's. dw's with the bell curve. The dn, I don't know why they do this in the book, because it's a Poisson distribution, but I suppose it's just a number as to how many times I've jumped in a time period. So a Poisson distribution has a shape more like that. It tells you how often something will happen in the next half hour, like how many buses are going to turn up whilst I'm waiting at this bus stop. Quite probably none. Might be one or two. Certainly 3 in some time period, and then getting more and more buses is less and less likely. So just another shape of numbers. So we can twiddle the parameters to choose how likely we are to jump. Pretty much the same code as before, but we're just going to bolt in this jump. Now I'm using the same engine for both of the distributions, and anyone who knows more about this than me would be interested to have a discussion about what impact that's having and if it's okay or not. I've convinced myself it's okay. It's certainly okay for this nice simple demo. Almost the same code as before. We're just going to multiply a jump size, which I've made configurable, so I can force it to jump out of the paper bag, times this number we get back, which in essence is going to be 0, which means we don't jump, or not 0, which means we do jump. Now, I could make it jump down, but we're trying to go out of the paper bag, so I'm only going to let it give me positive numbers back, and it's definitely going to work. Now, all right, so now we want one with jumps. That's not J, that's J. So kind of doing what we were before, but if we get back non-zero from our dn magic numbers, whang, it go up. This time, we've definitely got some stock prices out of a paper bag using a type of diffusion model. Well, I'm quite impressed. And that's nearly that. Let's just try one more. Yep, some more out again. So the jump diffusion works better. Of course, with just the stock price without the jumps, I could play around with the numbers and make sure it got out. Actually, there's some quite complicated maths hiding behind all of that. But to me, the message is, don't panic if we see some words like stochastic and DW and things. Frequently, if you actually get into this and try and implement it yourself, it will just be some multiplying, some adding up going on. Find a way to build things up simply one step at a time, test what you're doing. Things go wrong. All kinds of things went wrong for me. I mentioned some of them, and there were more besides. Have some fun. So what else could we do? Well, the paperbacks have all been two-dimensional so far. I'm sure someone like Guy could help me build three-dimensional paper bags all out of triangles or something. I could add a heat source that will make some move more near one side of the bag or the other if I want them to go in a specific direction. Something I've not played with yet is a firework algorithm, which sounds quite exciting, but that might set fire to the paper bag as well. Goodness. So, encourage you to figure out what coding your way out of a paper bag really means. Find some pet project to play with and just have a place that you can play with things, see what happens. That's about it. So we've done some Brownian motion, which is a type of random walk. As long as we've got some good random numbers, just adding them up, we moved. Geometric Brownian motion is quite simple to set up as well. That involves some multiplying. It's not so hard. I skip through the property-based testing. And again, if anyone does know a good C++ framework, please talk to me. I just want to play with more of this really interesting stuff. And the thing that I learned is that I can't remember how to use rand properly. I'm sure I did used to know, but I had to think and go, do I need a +1 in here? So don't do that. 10 entire minutes left. And you could code your way out of the paper bag too. And that's it. I'm going to set off the diffusion happening, and if anyone's got any questions, or didn't get a sticker and wants one, then let me know. And they're off again. As I said, they do take about 20 minutes. I'm told there's 10 minutes left, but if anyone's got any questions, let me know. If anyone wants to skip out early, that's fine. If anyone didn't get a sticker, I've got a few left. Any questions? SFML. Yeah, I think if you put that in your favourite search engine, you will just find it. Something like simple, fast, medium. I thought it was fast, but yeah. I'll make these slides available somewhere, and then you'll find a link for it. There's another question from here. Yeah.
So how can you sort of do it? We don't know what the thing is. We might just have some historic data as to how sort of moved in the past. How can you use that to sort of try and see the random modelling?
So I'm not. Yes, there is. And the other factor there is different people are trying to do different things. That's not true. They're all trying to make money. But some places like hedge funds will be trying to look for a new opportunity to make the money. So they look at historical stuff and go, well, previously when that's happened, then the prices have gone up or down. So they're trying to guess what's going to happen next. So the banks on the sell side are selling all these products will try and guess from any published prices on Reuters or Bloomberg how other people are pricing them. Because if they price the same instrument with a different value, then that creates an arbitrage opportunity. So they're looking at each other, trying to work out whether they've used LIBOR and how they've set up their model to make sure they all come out at the same price. But then that introduces a problem with the high-frequency trading and the front-running, where people are managing to get the numbers out quicker, or sometimes slower, because that gives you another way of doing some arbitrage opportunities. So are you trying to predict the future or guess what your rivals are up to? And that's going to change the maths you're doing. Are you trying to do things really fast or really slow? If you're a pension fund, which I don't know so much about, you've got a different perspective on things. So basically, they're making it up. I did the CQF ages ago, and Paul Wilmot makes a big point about all these models. You tend to run a long weekend batch job recalibrating every week. In physics, you don't recalibrate to see if acceleration due to gravity has changed since last week. When you get a model in physics, it works until you need a better model. You don't keep changing the constants that you're using in the model. The clues in the name, they're supposed to be constant. So I think you should start looking at how often people are recalibrating and how much the numbers are moving by. And that's actually quite an interesting thing to do in some machine learning. Look at the hyperparameters and see what variation you're getting there. Big topic. So that's another question. The naive, simple answer to that is because we're using the bell curve, you then go, well, do you expect the tails to be like that? And then you start saying, oh, fat tails, and VAR's not a good model. So essentially, almost nothing follows the bell curve, really. Even people's heights, that's wrong, and you should probably do some skullduggery of Poisson distributions to get that right. A lot of people are looking at kind of behavior analytics stuff and sentiment analysis, even for the trading things, because it does tend to tumble down like a house of cards. So trying to spot weird, spiky behavior that's going to just escalate out of control like some sort of positive feedback loops a thing. But I don't think they know what they're doing, and each time they think they sorted one thing out, then that provides a new challenge. So it's okay, it's kind of good enough for now, but yeah. And it's quite, the whole economy is a very complicated system. You can't predict the future. Shocking news. And if the stock prices are all random numbers, then you can't make any money out of the market. But I put that up as a disclaimer, the idea being that it is an efficient system and a zero-sum game clearly isn't true, because otherwise your pension would be worth nothing. Actually, loads of people's pensions are worth nothing, but that's because of fraud. So there's a question over here. No, I haven't. This sounds like fun. Oh, that would definitely get you out of a paper bag, wouldn't it? Say the name again. Diffusion limited aggregation. Oh, new toy to play with. Wow. Yes, no, some of the flocking systems are quite interesting. I've done some stuff with some swarms, but I've never had time to do the flocking ones. But yeah, great. Oh, I'm going to grow some trees the right way up. Yeah, some L systems are really cool. I made that AtQ t-shirt with a dragon curve the other year. Splendid. Yeah. It might go left, it might go right. Yeah. Different patterns every time. Yay. That's part of what I was trying to drive at behind the property-based testing. So the point, if you're doing a Monte Carlo simulation, you particularly want a number out, like the area of that squiggle. You need to run enough simulations to get quite a consistent answer, so you can look at the variation as well as the mean of what you're getting. But if you start looking at some of the properties as well, that gives you a sideways look. So it's not necessarily reproducible at that point. You're going, is it giving me the kind of properties I would expect from the model I've built? Or you can use the same seed and see if you get the same numbers out. But I'm slightly suspicious of that, because then people are just checking they get the same numbers back, and they don't spot some obvious things. One of the places I worked at several years ago, a very clever maths guy had written some code to price some interest rate swaps or something. And I turned the volatility off, and it should have been a continuous function. It went like that, and there was this jump. but he was piecing bits of curves together to make a piecewise curve. He said, but that's totally unrealistic, having no volatility. How dare you test it under those conditions? No, but it should not be jumping here. There's a problem. And he'd gotten off by one error in one of the for loops, but getting rid of the randomness let you see some of the skeleton, the shape of what's happening underneath. So yeah, that's a problem, but I think people tend to look at it the wrong way around. If you've got a complicated maths model or machine learning model, make all the parameters 0, and then you can probably work out in your head what should happen. That's a test case. Do it. Right. Yeah. Yeah, so is anything actually random? And loads of questions like this. I think on that point, my time's near enough. Thank you for listening. If you didn't get a sticker, there's stickers.